Okay, so let's move on. All right. So this I've taken you guys through this thing before over and over again. So I'm not going to waste time. Okay, we've seen this over and over again. I'm not going to waste time. All right. So at the end of the lesson, students or candidates should be able to know and understand one the program life cycle. Please, ICT is different from computer science. I've said this over and over again. There are certain things in ICT you don't bring it to computer science. You can, transfer certain knowledge like input device, output devices to computer science. But there are certain things are only specific to computer science. So when I say that this thing is specific to computer science, please kindly take notes. Don't go and bring computer ICT knowledge to certain, computer science. Uh, they will mark you down. I have to be honest. They will mark you down. Okay. All right. So at the end of this class, you should be able to what? Understand and comprehend the program life development life cycle limited to what? Analysis, design, coding, and testing. Then every component is made up of what? Subsystems. We talk about known as what? Decomposition. Then the purpose of what? A given algorithm. That means if I have an algorithm, can you look at the algorithm and tell me what this algorithm is actually doing? And what is even algorithm? We'll talk about it. Then the standard method of solution. Then the need for validation and validation check. Why? We've done this already in ICT, so we can transport the same thing. Suggest and apply suitable test data. We'll talk about the test data. In computer science, we add another one to it, making 4. In ICT, I think we dealt with only 3. So was it 3 or 4? We'll find out. Then we have the trace table, then identifying errors in a given algorithm and suggest ways of correcting these errors, and how to write and amend algorithm for a given problem and scenario. Please, those of you who are me, and not all of you, you need to practice this over and over and over again. Okay, you need to practice. When you go to Papa Cambridge, you have a lot of Pasco over there. Go and practice, especially from here. From this part, trace table, this and that. When they write an algorithm for you and ask you to identify an error, you need to be somebody who has been doing this over and over again to be able to what? See, there's an error in the code, there's no error in the code, like that. Okay, so the program development life cycle. In ICT, we learn this. How many steps do you see in ICT? I think almost how many? 9 or what? About 9 steps. But in computer science, it's only 4. It's only 4. Okay. Now, it's the same thing, but it's a little bit different. So that's why I said don't go and bring some certain things we did in ICT over here. Okay, here we are not going to talk about the piloting, the parallel, the changeover. No, we are not interested in that. We are interested in basic things such as decomposition. So in ICT, we didn't say anything in regard to decomposition. We are going to talk about something such as abstraction. In ICT, we didn't talk about abstraction. We're going to talk about something such as structure diagram, flow charting, pseudocoding. All these things are needed in the program development life cycle. In ICT, I didn't mention that. In ICT, our main tool was what? Our main idea was to learn basic things that will let us implement. But in computer science, we are going to build the things ourselves. So we need to understand how the program development life cycle is. All right. So what is it? It's a process that developers follow in order to create a new program, or can also be a system. It's fine, either a program or a system. It's a cycle, not a linear process, because after developing the software, it is often necessary to go back to the start of the process again if something has been discovered during development. This, we spoke about it in ICT. Okay, we said it's a cycle in ICT. I can even show you the waterfall. That means you can go back and forth till what? You get the correct thing or you get the correct system. Okay, so it's a cycle, not a linear process. That means you are not moving from step 1, then step 2, then step 3. No. It's not like a school where we go to class 1, they move to class 2. No, somebody in class 5 can come back to class 1, come and learn. That is how the software development life cycle is. We can go back and forth till we get the work done. Okay. So when you talk about the software development life cycle in computer science, this is what we are interested in. First, we start with the analysis. Second, we do our design. Third, we code. Then, fourth, we test. Coding is the same as implementation. So either you see coding or what? Implementation. So we are implementing. In computer science, there are only 4 levels. We do analysis, we design, we code or we implement, then we test. We don't have any implementation there. We don't have any documentation here. No. We'll talk about how to write maintainable program later on, but you won't find them over here. So can you take note of this? All right. So what is the analysis? It's the same thing we saw in ICT, but we are going to focus more on 2 important things. Okay, it's the same thing. You want to analyze the system requirements, user specification, all these things. But in computer science, we are going to focus on 2 important things in the analysis stage. 2 important things in the analysis stage. What are they? All right. So before any problem can be solved, it needs to be clearly defined and set out so anyone working on the solution understand what is needed. Okay. You remember in ICT, I spoke about requirements, specification, all these things. In computer science, our focus is not going to be on that. Our focus is going to be on these 2, abstraction and decomposition. Now, each stage in the software development lifecycle, we have certain things that we do. So in the analysis stage, 2 things that we do is abstraction and decomposition. We'll talk about what is an abstraction, what is decomposition. So in analysis, we need these 2 tools or these 2 concepts to be able to get to know everything about our system. First, we do abstraction. Second, we decompose. So kindly take notes. In the analysis, these are the 2 methods or 2 approaches that are used in the analysis stage. Abstraction and decomposition. What is abstraction? What is decomposition? Let's dive into that. When you talk about decomposition, it's like you are breaking down a complex, not that it's a way that we break a problem or a complex problem into smaller parts, which can then be self-divided into even smaller parts that can be solved easily. Let me explain this. There's an adage in P. They said that if you take your time to cut the ants, you can get it intestine. You can see it intestines. There's a proverb like that. Okay. Now, in computer science, when we are solving a problem, we don't jump on the problem just like that. You will get lost. You will get tired. You know where to start from. So what we do is that we decompose the problem. Decomposition means you are breaking the problem into manageable pieces so that you can tackle each sub-problems. So you can decompose and keep on decomposing. I don't know whether you've heard me using this word, divide and conquer. They use something else, so divide and conquer. So you divide and you conquer. So you divide the problem into several sub-problems. Then you can get to the base. We call it the base. So if you get to the base, you can now solve the base. As you keep solving the base and moving up, which is from, we call it, that which term do I even use? Top up, is it? No, you have the down, top down. Oh, there's a term they use, it has skipped me. Okay. So let me even try to draw it for you to see. Okay, let me use here. So we have a bigger problem like this. Okay, if I want to solve this, I have to divide it into 3. So this is 1, 2, and 3. I can pick problem 1 and also divide it again, maybe into 2. Okay, then I can also pick this and divide. So I'll keep on dividing till I get to a place known as the base. The base is the level where the problem cannot be divided or you can't divide it again. Once you get to the base, you are done solving the problem. Anytime you want to solve a problem in computer science, that's how it is done. You don't jump. You do something as what? You decompose the problem. You break the problem into smaller pieces so that you can solve it. If you have a bigger problem and you jump straight away on it, you will get lost. So decomposition is what we breaking down what problem into manageable pieces so that what it can be solved. The next one is abstraction. So abstraction keeps the key element. Now, when you are solving a problem, sometimes there are certain important things that we need. Others we are not interested in. Okay, so anytime you hear the word abstraction, it means we are paying attention to the important things while neglecting the unnecessary ones. For example, if I ask my firstborn to prepare me a tea or a coffee, okay, a cup of, a tea or whatever, he's going to solve the problem. So the problem that Valerie is going to solve, first, he has to decompose it. That means he has to get the tea, water, everything. That's decomposition. So you have to get all those things. Then the next one is you need to abstract. Now, he's going to get me a tea. At the end, what I need is what? It's a cup of tea. So whether the cup is big, the cup is small, the cup is yellow, the cup is blue, that one is not my problem. At the end, I need tea. So it's like the size of the cup or the mug or the color of the mug. Those things are all not important. They are not necessary. So we abstract them. I don't know if you get me. We abstract them because the color of the mug has nothing to do with the tea. What I need is the tea. So if you are giving me a white mug, that will not make the tea special or make the tea taste better. So in abstraction, we keep the key elements required for the solution to the problem and discard any unnecessary details and information that is not required. Okay, so abstraction is the process of selecting the information in a problem and focusing only on the important parts of that information. So anytime we abstract, our main point over here is what? We're looking at the important things and neglecting what? The unnecessary ones. I don't know if you get me. Okay. We look at the important things whilst we neglect what? The unnecessary ones. Okay. So in analysis, these are the two: decomposition and what? Abstraction. Okay. So let's look at this. So a person wishes to make a cup of tea. What's the information that you need? You need tea bag, milk, sugar, whatever. What are the abstracted information? We can ignore the color of the mug. That is not relevant. What again can we abstract over here? The size of the mug, right? We can abstract that. What again? What can we abstract again? What can we abstract? If you look at the information over here, there are certain things we can abstract. They are not going to, we don't need them. What can we abstract? What can we abstract, guys? Come again?
Or brown sugar.
Yeah?
Whether the sugar is white or brown.
Yes, the color of the sugar.
White or brown sugar.
Thank you. The color of the sugar. That's not a problem. What we need is sugar to give us sugar. What again can we abstract?
The brand of the kettle.
Come again?
The brand of the kettle.
Yes, the brand of the kettle. Okay, we don't care. What we need is what? We just need a kettle to get us hot water. So the brand of the kettle, we can abstract it. We are not interested in that. What again can we abstract?
The type of milk being used.
Yes, the kind of milk. Whether it's carnation milk or ideal milk or whatever milk, what we need is milk. So if you look at it, there are a lot of things we can abstract. For example, the tea bag like this. Somebody will use lifting another person. What we need is a tea bag. So get us a tea bag. So you see, that is how computer scientists solve problem. Okay, when you are solving problem, you don't focus on. We want to go into the detail. You can't solve it. What I need is a cup of tea. Get it for me. That is all. Okay, so after you've gotten it, then we can now begin to think about other things. Okay, so that is the importance of abstraction. Paying attention on the important things whilst neglecting the unnecessary things. That is abstraction. All right. So decomposition. So here, decomposition, as you can see, we decompose the thing to get our water, combine, personalize, and serve. So how do we get the what? I mean the tea. The person say, okay, maybe I have 4 steps. First thing, I have to get the water. Second, I have to do some combination. Third, I need to personalize. Fourth, I need to observe. So what a person has done over here, decompose the problem. So each one and what the person is going to do. That's decomposition. Okay, decomposition. And that is what we are going to use. Anytime we are solving any programming problem, you need to state the problem carefully. Start writing things down. That is something that I'll be beating some of you. You write things down, you decompose it, you abstract things, and be able to solve the project or come up with a project, a solution to it. Okay. So that is that for analysis. The next one is design. Now, design, this is one of the most important. Why? Because your creativity, how creative you are, how sharp you are, your thinking, everything have to fall in here. How you are thinking, have to fall in here. Because it is your design that is going to give us the end product. Because how you are designing it is what will inform the programmers. Because the programmers will be waiting for your design. So once the programmers get your design, whatever you present to them, that's what they are going to sit down to program and submit it to us. So the design, a lot goes into it. A lot goes into the design. If I say a lot goes into it, it means you're thinking. This is where we see people who are creative. Okay, so let's look at what are some of the factors or what are some of the methods that we have to look out for when we are designing. Okay. So here, the developer of the program will continue the decomposition phase from the analysis and begin to draw up visuals of the end of the product. So visuals are what needed over here. This includes structure diagram. So the structure diagram that helps to visualize the end goal. Then flow chart. So do something known as flow charting. So flow charting that shows how a program decomposes, part will run, including any decision or input that are needed. Then the 3, pseudocoding. Now, the paper 2, we have 3 different languages that we are supposed to use. We use pseudocoding, we use Python, we also use VB, Visual Basic. Okay, pseudocoding, Python, and what? Visual Basic. Okay, now here I decided to teach pseudocoding. Okay, others will teach Python, but I'm teaching pseudocoding because pseudocoding is similar. Those of you go and do, computer science at the university, you guys will be introduced to C and C++. That is the first programming language you guys will be taught in school. And pseudocoding is closer to that. It's almost the same as C. So once you get a concept, programming will be much easier for you. Okay. So these are the 3, methods or approaches that are used in the design. We do our flow charting. So we do our structure diagram, we do our flow charting, then we also use pseudocode. So the flow chart, I'll show you an example. Pseudocoding too, I'll show you an example. Then the structure diagram too, I'll show you an example. So I'm going to take them one by one, dissect them, and find out more about them. All right. So this is a flow chart. Okay, this is a flow chart. So you have different symbols. I remember I gave you guys something to do where I asked you guys to go and read the year 10s, the year 7s live. Some of you did, others didn't. So those of you who read it, definitely you will tell me what each symbol over here is. Okay, and this is what we'll be drawing. You guys will be drawing. In the exams, they can ask you to draw or they'll draw for you and ask you questions on it. So this is a flow chart. Okay. Then the next one is coding and interactive testing. So if you look at the coding, I said the same thing as what? Implementation. As you can see, same thing like implementation. The one thing about coding is that you don't just code and you are coding and coding and coding. No. As you are building the modules, you are doing what known as interactive testing. You are testing alongside whilst you are building. But the testing, we have the original testing over there, which we'll learn about, known as integration testing and unit testing. We'll talk about it. But whilst you are programming, you are also what? Testing alongside. Because you can't just write the code and think that everything is working fine, then boom, you go. Share. You test as you are writing. You test as you are writing. You test as you are writing. Okay. So this is sometimes known as the implementation stage, as I said. The programmer works on a design module such as the input-output processes and write the code to make each part of the program functional. Iterative testing means that, did I even say, okay, this one, okay. Iterative testing means that modular tests are conducted, code amended, and tests repeated until the module performs as required. Okay, yeah. Okay, I think the word shouldn't be interactive. It's supposed to be iterative because it doesn't make sense to be interactive. Iterative, yeah, testing. That's what I was trying to explain. Okay, so coding and what? Iterative testing. So here, as I did explain, okay, whilst you are coding, you are testing. You are amending the modular and all sort of things. So till whatever you're interested in, what you get. Okay, so you don't just code. You code. By the time you finish, you have a lot of bugs, errors in them. Okay, so as you are coding, you code this part, you test it to make sure it works. You code this part, you test it to make sure it works. You code this part, you test it to make sure it works. Till you are done, building your system. So after you are done, then you now come to the full testing. So when you have finished your program, you need to carry out testing to make sure. Why do we carry out testing? To make sure the system fully works. The system do not crash, meet all requirements. Why do we do testing? To make sure the system works. The system do not crash. Now, what's the difference between when you say the system fully works and the system do not crash? Now, one of the things that you see is in mathematics, you don't allow division by zero, right? In computer science also, I don't know whether I asked you guys to go and find out from Sir Eugene. Why is it that in maths you don't allow division by zero? Did I ask you guys to go and find out? Did I ask you guys to go and find out? Hello? Kama? Valerie? Joy?
Mm.
Did I ask you guys to go and find out why in maths you don't do division by zero?
I don't think so.
Okay, so when you meet Sir Eugene, you are supposed to ask him. Let me
I
explain it to you.
don't think so.
Let him explain it to you. When the next time I meet, I'll take the answer. Why is that in mathematics you don't do division by zero? Okay, yeah. So when it happens like that, your program can crash. Although your program is working, well, but it will crash because there are certain things we don't permit. For example, division by zero. For example, if you want to find the log of a negative number, we don't do those things. So your system will crash along the way. Then also meet all requirements. So testing every part of the program requires what? A test strategy. Okay. Now, first, the entire system divided into small sessions that are tested for input, output, and validation rules. Okay, so we do this to make sure the validation rule, everything is all working on well. So the entire system divided into small sessions that are tested for input, output, and validation rule. Validation rule, we'll talk about this in computer science. But in ICT, we spoke about it. I remember, okay, where we talk about the data type, we talk about the presence, all these things are checks. So they are checks that we we actually carry out on what? On your data. All right. Test data is used for all of the tests to be carried out. You'll be talking about the different test data too as well. Then unit testing, okay, this one is where we try to test each part of the code individually. So when you're talking about unit testing, they are talking about the modules. Talking about the modules. So for example, the input module, the output module, the processing module, that is talking about the unit testing. Okay. Then the integration testing is testing the entire program when all the individual programs has been combined. So know the difference between the two. When you are doing your unit testing, when you are what? Doing integration testing. So integration testing is trying to bring everything together. By unit testing, you are testing on different parts of your module. Different part of your module. So before you bring everything together, that becomes what? Integration testing. Integration test. Are we okay here? You guys are quiet too much. Are we okay?
Yes.
Yes, please.
Yes.
Okay. If you're okay, let's move on. All right. Now, before you do any testing, you need test data. Okay. In ICT, we had three, right? We had three. But in computer science, we have four. You can take notes. In ICT, we had three, but in computer science, we have four. So you need to identify the appropriate test data to use to test the program. So there are four types of test data. The first one, we have normal, as we saw in ICT, the same thing. Abnormal, as we saw in ICT, the same thing. Now, extreme, as we saw in ICT, the same thing. But boundary is what is what? Different. So when we talk about a boundary, we are talking about the data that is on the edge of being accepted and being rejected. Extreme is at the edge of what is allowed. And extreme you already know. So we have an example and you see it. So extreme is talking about, what is at the edge and what is allowed. But a boundary is talking about what is what? Accepted and being rejected. That means in a boundary, you need two different types of data to specify your test data for boundary. You don't need one. Normal, you need one. Abnormal, you need one. Extreme, you need one. But boundary, you need two. Because one of them has to be accepted, one of them has to be rejected. So we normally put it in or. So this or that, or this and that. I think it's and rather, not or. Let me confirm. That you use and. Okay, so let's see. Here, a program allows the user to enter their age as a whole number between what? 10 and 100. Normal data, any of this is go. That means this inclusive. Abnormal, anything outside. Extreme, you see the extreme, you can pick 100 or 10. Okay, so that means this, we said is at the edge or what is allowed. At the edge of what is allowed. So since we are saying it is 10 or what? 100, these are extreme. But let's look at the boundary. So the boundary, the definition is saying that data on the edge of being accepted and being rejected. That means one of them will have to be accepted and one of them has to be rejected. So here, if you should consider the 100, then it becomes what? 100 and what? 101. So it comes together. And is very, very important for the boundary. And then let's look at it down here. If I pick the lower point, okay, it down is going to be all right. So I was talking about the boundary, okay, the boundary by saying that the first three is the same thing as we saw in ICT, but the boundary is a little bit different as it reports what? Two values. One at the edge of being accepted, one at the edge of being what? Not accepted. So as I show you, if we are supposed to enter 10 and what? 100, then let's look at the two values, 100 and what? 101. If you are supposed to enter so 10, if you are picking the lower bound, then it's going to be 9 or 10. So can you take note? One of them has to be accepted, one of them has to be rejected. The one that is being accepted must be at the edge, must be at the edge of what is being accepted. And one has to be rejected at all. Okay. So let's look at this. So here, a user needs to enter a password at least 8 characters long. So at least 8 characters long. So this is correct, this is correct because at least 8 characters long. Abnormal, 7 characters. So 1, 2, 3, 4, 5, 6, 7. So this is normal, this is abnormal. And extreme, we can pick exactly 8 characters. Exactly 8 characters. And boundary, okay, one of them will be accepted, one of them will be rejected. So this is 7 and this. Okay, so this and that, any of them. So here you put the n over here. Okay, then here you put the n over here. Okay. Is this clear? Is it clear?
Yes, please.
All right. When is the class ending? Are you going for 1 hour or 1 hour 30 minutes?
Say 1 hour.
Me pay 1 hour 30 minutes. But me say me yes you answer. My beg you call. Mo make kasa mo dia mo kasa bi. All right. So let's look at the computer systems. Okay. This one of you already seen it before in hardware where we see the computer architecture, right? So we have the peripherals, the input and the output. Then we have what the processor, which include the CPU and the RAM. Sorry. Then we have what the storage too as well. So that's the computer system. Now in the analysis stage, we said what we can decompose, right? If you have any problem, we can decompose it. Once we decompose it, we can get all the way to the base. Once we get to the base, we're able to solve the problem, right? That's what we learned. So let's look at it. So all computer systems require inputs and processing and outputs. Also linked to this processing is the storage, which enables data to be used as and when required. Okay, each computer system can be divided up into a set of subsystems. So remember the computer system you are seeing over here, the people who came out with it. Okay, if you take the input, the output, and the processor, okay, as a system, we can take only the input and also have a subsystem under it. That is why even the input we have what? The manual data entry, we have what? We have the direct data entry. That's the subsystem. We can take the manual and we see one of them that we push, the other one that we click. So when you have the system, we can put them into subsystems. Okay, and even subsystems can also be further be divided into subsystem. If you have a subsystem, we can further divide it into what? Subsystem. Okay, so you can have a subsystems and even further divide into what? Subsystem. You get it? So it's up to you. It's up to you. Okay, it's up to you. And this is where, as I said, creativity and all these things comes because of the way computer scientists solve their problem. Most of the time, okay, you see them drawing on the wall, drawing on the board, all sort of things. But at the end, they have their problem solved. So that is the problem in the composition. If you look at it, see the way, forgive me, the teacher, I took it from Adobe stock. So pardon me, because I put it on YouTube. You should pardon me or else they will hijack me. Okay. Oh, so look at it. Look at how nice it is. See, they decompose the thing nicely. You get it. So that's problem decomposition. All right. Now, any problem that uses a computer system for any solution needs to be decomposed into what? Component parts. So he's saying that if you are going to solve a problem, and this problem that we are going to solve, definitely we are going to use a computer system, or we are solving the problem for a computer system. That means we need to decompose the problem into these 4 stages: the input section, the processing, the output, and the storage. As you can see, the inputs, the processing, the output, and the storage. So what he's saying is that I have a problem. This problem, it will be implemented on a computer, or I'm going to use a computer to implement it. Definitely, I need to decompose the problem into 4. Tell you that where is my input part? Which part is going to be the input? Which part is going to be the output? Which part is going to do the processing? Which part is going to store? So once I do this decomposition, It helps me. So I can write only code, only the code for what? Input. I can write only the code for the output. I can write only the code for the processes. I can also write the code for what? For the storage. I can do this. Do you get it? So I have different parts. Okay. So that is how when you're solving a problem for a computer to process or to use, or when you are trying to implement any problem using a computer, you need to note your input part, the output part, the processes, and the storage. Okay. So what are the input part? The input part talks about the data used by the system that needs to be entered while the system is active. Okay, so we are thinking about the input data. What data are you going to enter? Then the processes, the tasks that need to be performed using the input data and other previously stored data. So what computation? So for example, if you want to have um, a velocity app, what's the formula for velocity? What's the formula for velocity? If you want to find the velocity, what's the formula? If you want to find the velocity, what's the formula? What is the formula, my people? Hey, are you not on a call?
So we didn't hear you. What did you say?
You want to find the velocity of a moving body. What is the formula? Yes, Kayla, I didn't hear you.
Displacement over time.
Okay,
Total time.
displacement over time. So V is equal to what? S over what? My T. V is equal to S over T, right? All right. So V is equal to S over T. That is. Now, what is going to be the input? My input is going to be what? My displacement and what? And time. That's going to be my input. The process is this calculation. That's going to be my process. Me dividing the displacement by the time. That is going to be my process. Then what is going to be my output? How do I output my message? Maybe I can show it on a screen. I can print it for you. Then, having done that, maybe I want to store it for future use. So I can store it on any of the disk or the storage devices. So you see, we have our input, you have our processes, you have our output, you have our storage. So when you're solving any problem that will use a computer, or when you're solving any problem for computing purposes, you need to make sure that you need to divide it into all the input, the processes, the output, and the storage. Okay. Any question?
No.
Okay. So we've already seen the pseudocode. We've also seen the structure diagram, also seen the flowchart, and which part or which level of the software development lifecycle do we implement the pseudocode, the structure diagram, and the flowchart? Salifu,
I didn't hear you well.
you didn't hear me?
I didn't hear you well.
Hey, Masa. You make us say, I won't in Ghana, I will do with some is a wound, you know. Me see, me get you now. I said the pseudocode, the structure diagram, and the flowchart. Which part of the software development life cycle do we implement this?
Testing, implementing,
Which part?
or coding.
Huh? You are not
Coding.
getting my question. There are certain method over here: pseudocode, structure diagram, flowchart. I said we have 4 development life cycle in computer science. Which of them do we implement these things over there, or do we apply these things over there? You get a question now? Hello? Salifu, you're not getting me?
Yes.
You're not getting me?
Um,
Okay, Marina, if you can explain it yourself.
the design.
Okay, it's a design. Thank you. It's a design. Thank you. All right. So at the design stage, we said we implement these methods, okay, to our design. We start pseudocoding. We also do structure diagram, also do a flow chart. So we're going to talk about them. Then I think I'll pause when I'm done with all these things. I'll not go on with any of them. I'll not go on. So I'll talk about all of them. We'll talk about pseudocoding, and that is all. I'll give you guys classwork to go and do. Okay. Yeah. Yeah. So I'll pause over here. The rest I'll give you guys as classwork to go and do. So when you do it, take a picture of it, send it to me via WhatsApp to look at it. Okay. So we said the pseudocoding, the structure diagram flowcharts are implemented during what? The design phase. Okay. So we're going to take them one by one and dissect and understand much or a lot about them. So let's talk about flowcharting. So if you want to show visuals or you want to come up with visual representation of how your algorithm is going to look like, we use what? Flowchart. Okay, so a flowchart is a diagrammatic representation of an algorithm. A flowchart shows each step of a process in the order that each step is performed. Okay, so it gives you like in a sequential way. So step 1, then step 2, then step 3, step 4, it goes like that. Okay, so a flowchart shows each step of a process in the order that each step is performed. Okay, so each shape has one statement within it. We are going to talk about the shapes. One of the things you have to note about flowchart is that we use shapes or symbols. The symbols, they have meanings, okay, and they have statements in them. And these statements, the symbols are joined, or the shapes or the symbols are connected using arrows. The arrow shows you the flow or the direction of the flow. Shows you the flow, the direction of the flow. And the content inside each box can be written as words or as pseudocode statement. Okay, so you can write it as words or pseudocode statement. Okay, so that is the flowchart. So you represent what? The diagrammatic, of your algorithm, how your algorithm is going to be. And it's a sequential way in the sense that step 1 goes to step 2, then step 3 goes, they have what? Different shapes or symbols, and they are connected by an arrow. The arrow shows you the flow or the direction. So this is a typical example of what? Of a flowchart, where if you look at this one shape over here, this one come down, there's another shape, another one. Here when you come here, you make a decision that we go here or here. Then we come and reach school. Okay. Now one of the things about flowchart we talk about is that all flowcharts need to have a start and need to have an end, because we are representing an algorithm diagrammatically. And one thing about algorithm is that they are finite. Okay, any algorithm you are working with is supposed to be finite. The algorithm needs to start from somewhere and end somewhere. It starts from somewhere and end somewhere. So anytime you have a flowchart and the flowchart doesn't have a start and doesn't have a stop, forget it. It's wrong. Okay, you lose mark for not including that. You lose mark for not including it. Are we okay? All right. Let's move on. So these are the symbols. So we have the start or the stop, the same thing. We have the process. Look at the symbol of the process. It's a rectangle. Look at the symbol for input and output. It's a parallelogram. The input and output, they have the same symbol. Then you have the decision. The decision is diamond. Then look at the subroutine. We'll talk about subroutine. Subroutines are talking about functions and procedures. We'll talk about it. So look at how the subroutine is. And look at the flow line. So these are the shapes we are going to use at your level. These are the shapes. So the start and the stop. The start and the stop is like over. I mean, some of these things, they don't expect you to, you're not computers that you can draw it perfectly. But make sure it resembles, anytime you are drawing, make sure what? It resembles it. Okay, so the start and the stop, the process, the input and the output. We have the parallelogram, which is for input and output. We have the decision, which is the diamond. You have the subroutine, and also have what? The flow line. The flow line shows what? The direction of the flow. Okay, let's move on. All right, so look at the start and the stop. One thing about the start is that you see the arrow, they start from the start and it terminates at the stop. Okay, so it is only one. Have you seen it? So it starts from here, then it gets into that. That's the start and the stop. We'll learn how to draw this. A big problem. Then let's look at the input. You see, one goes in, another one goes out. One goes in, another one goes out. The same thing, okay, for the input. And these are the decision. The decision has one coming in and two going out. These are the decision. One coming in, two what? Going out. This is, if you remember when we were in school, we were dealing with the if statement. Okay, anytime you implement an if statement, you implemented what? A condition over there, a diamond. That's the diamond. So if the age is less than this, if it is yes, pass to the left. If it is no, go to the. So that's a diamond. Okay, and we use what? The relational operators. You pay attention to them. They are all here. These are the relational operators that we are going to use. The equal, the greater than, the less than, the greater than or equal to, the less than or what? Equal to. We can also combine, but that one will be later when we are talking about Boolean. We can combine some of them using the or and the and. Okay, we'll talk about them, okay, as time goes on. Are we okay?
Yes.
Okay, so let's move on. Then we have the output. We got the output. One goes in, one goes out. We'll learn how to write, I mean, all these things as time goes on, but just study the shapes. The shape that is important. Then we also have the process. The process is a rectangle. This is what we used to do mathematics, print, I mean, not print, but do all sort of things over there. Okay, we'll learn it as time goes on. Right. So this is a flowchart for a calculator. If you look at it carefully, you see, let me hide this. Now, if you look at it, this is the start. Okay, look at my stop. Now, somebody is wondering, but say here, look at you have 1, 2, 3. No, I don't have 3. I have only 2. When you check the input, one goes in, one goes out. Okay, so the output, when you check the output, one goes in, one goes out. But here, somebody is wondering, but say we have 3, 1, 2, 3 here. No. The reason I'm getting 3 is because of this condition. This condition, this condition, this condition, and this condition. Because what is actually happening here is that if the condition is yes, we park here and come here. So if this condition is true, okay, we come here and we come here, then we end here. So all these things will never happen. That's the meaning. If this condition is yes, we pass here, then we're going to choose this path and come here and come here. So all these things will fail to exist. But if this condition is not true, but it is no, we ignore this line and come here. When we come here, if this condition is yes, we will take this path and come here, we ignore this one. Okay, so at any point in time, the output has to have a one going in, one going out, if you trace it well. But somebody is wondering, let's say, that is what I'm trying to demonstrate over here. That as you go through it step by step, you see that they all have to satisfy what is in the table. Okay, it is only the decision that has what? One going in, two going out. Apart from it, the rest they all have what? One going in, one going out or coming out. Can you take note? But the way you draw it, I mean, you see I'm connecting two, which is one here, then two here, and even 3. So somebody is thinking by saying you have 2 going in. No, it's only 1, depending on what? The path over here. The path over here, that actually what? Do that. Are we okay here?
Yes, sir.
Is it clear?
Yes, sir.
Okay. Now let's look at this. This is another one. Okay. So here a flowchart for password validation program. So we tell the person to put a password, then we check. Now anytime you see the line going back to the start, we call it a loop. We'll talk about it. That is a loop. That means it will continue asking you over and over again till you do the correct thing. So if it is no, you go back. You go back. So this is a loop because it takes you back to the start. Okay, it takes you back to the start. So anytime you are entering your password, and you enter the password, it tells you wrong. It's a loop you are in. If you don't get the password correct, it will not open for you. And nowadays they made it I think 3 times or 4 times. To block you. So you've been in a loop for 3 times. Okay, you've been in a loop for 3 times. So that is that. So go here all the way to this place. Go here all the way to this place. Okay. So that is that for that. If you have any question, you can ask me. Please don't feel shy, and don't be quiet. If you don't get anything, let me know. So that is that for your flowchart. So we are done with that. The next one is structure diagram. The structure diagram. Structure diagram. Now, if you look at the structure diagram, that one resemble what we spoke about with regard to the the decomposition thing, which is, this. We use the structure diagram for this a lot. Okay, we use the structure diagram for this. Okay, but hardly do we use the flowchart. Okay, the flowchart just shows you the diagrammatic of the flow of your program, but it doesn't go to that level. So the structure diagram can do. If you look at it, you see we have the system over here. Then we have the subsystem 1, subsystem 2, subsystem 3. We cannot divide the subsystem 1 into what? Subsystem 1, 1, subsystem 1, 2. So we can even go ahead and divide this one again, and divide this one again, and have it like this, and have it like that. So we can go on. Okay, now when we finish, we try to code them. So we write a program only for this, write a program only for this, write a program only for this, write a program only for this. Then after that, we put everything together and we have what? A complete system. Okay, complete system. So it is used to show top-down design. This is the word I was looking for. We have the bottom up, we have the top down. We call the bottom up, we also have the top down. So it used to show the top-down design in a diagrammatic form. This word, how do you pronounce this? Ms. Boabeng, how do you pronounce this?
Hierarchical.
All right, so hierarchical, thank you. So they are hierarchical, showing how a computer system solution can be divided into subsystems, with each level giving a more detailed breakdown. Okay, so it is developed by decomposing a program into sub-programs. Okay, so the decomposition, this one is far better for decomposition, structure diagram. So it shows you what a top-down design approach. So the diagrams has the name at the top, and below is all the sub-programs. Each sub-program can be split down further if it is what required. So it's up to you till you get to the base. Once you get to the base, you are good to go. Okay, so this is a structure diagram for a calculator. This is a structure diagram for a calculator. But let's look at it. Do you think I can further divide some of them? Do you think I can further divide some of them? Or I should pause here. This is my calculator. So are you talking? I'm not hearing you. Hello? Who is talking? Mm. Salifu, Marina, you think I can further divide
Yes.
or I should stop?
I think
You think what?
I think you should stop.
I should stop here.
Mm,
Okay. My firstborn, what about you? What do you think?
So when you're saying further divide, you mean like the processes,
Yeah, if you
like
look
the
at
ones
the
that they've
input,
listed
the
by you.
process, and the output, can I mean, subdivide them or I should stop here? Because I'm drawing a structure diagram and we said that one you can decompose, right? And I'm saying that this is my structure diagram for a calculator. I said, is it okay for me to leave my structure diagram like this or I can go further to divide it? I mean, decompose further.
So if you decompose, what will you decompose it into? Like if you had to decompose it.
Oh, so I should not, I mean, decompose again. I should pause here and present this one as my structure diagram for
No,
my
but will
calculator.
it be okay if it's like this? Like
Oh no, but you are the one developing a calculator. So if you think you can program, I mean, the input, the process, and the output like this, I mean, we can leave it like that. Hmm? Tama, what do you think?
so you should be decomposed, right?
I should decompose it. Okay. Tama, what do you think?
So I think you should further divide.
I should further develop, I mean, decompose it. Okay. Yeah. So one thing about a structure diagram is you need to keep decomposing till you get to the base. Okay, we can't leave, I mean, this diagram like this and present it as our final answer. No, not our final answer, as our final, I mean, method for the programming or the coding aspect. No programmer will be able to do this. No programmer can program when you present a structure diagram like this. They will get confused because the input also has parts. The processes also has parts. The output also has parts. So we need to go one step further and break it down. So what do you think we can do for the input? The input we can say, okay, we are going to take input number one, then we input the symbol, then input number two. So the input has been further or subdivided into what? Three different inputs, which is the number, the symbol, then the number two. Isn't it? Then let's see the process. Now, what do we want to do? The process, either we add the two numbers, as you can see over here, or we subtract, as you can see, or we multiply, as you can see, or we divide. What about the output? What do you think I should do to the output? Who can tell me? Having seen the input and the process, what do you think the output should be? Or what further division should it be? What
Steffi,
further?
can I try?
Okay, go on, Joy.
I need to do output symbol and then number. For example, if it is a negative number, then come up to the negative sign and in the number.
Output, symbol, and number. But if you're using your calculator, what do you normally? What is? I mean, just imagine how you're using your calculator. So how do you think the? I mean, the output for your calculator? How does it present to you? Go look at how the presentation is done. That is what is important. Mm. All right. So the output, I mean, we won't need anything. All we have to do is we can just put something here and say what display results. That is all. Or output results. We are not going to, have any different output. Okay, we just display our results. So that means display the results from here. We just display our results. Okay. Then let's look at this. The alarm app. Okay, so when you have an app, hey, our time is up, eh? People, oh guys, is it our time is up? Oh, okay. Then let me pause here. Okay, we'll continue the next time that we meet. Okay, are you okay? Are you okay? Hello, guys. Are you okay? Hello.
Yes, please.
Okay, so we are going to stop. Okay, because we are going to break out right now. Exit the breakout room, and that'll be the end. So when we meet again next time, we'll continue from there. Okay. So the next time I'll give you guys the work.